For decades we were told the moon was a dead, silent rock. But inside its darkest craters, scientists have found something shocking: ice that could fuel rockets, and an invisible force that could cripple them. These frozen pits hold the key to building a base on the moon, but they may also be the most dangerous places any astronaut has ever stepped. Why? Because the shadows hide a deadly electric trap. Join us. The danger of the permanently shadowed regions. The most dangerous place on the moon is where the water is. That chilling warning, said to come from a NASA insider, sounds impossible at first. For decades, scientists dreamed of finding water Earth, and when missions finally proved the moon had hidden reserves, it was celebrated as the key to colonization and the future of deep space travel. But what if those icy vaults are not a gift at all? What if the very places we thought would save us are actually silent death traps? And if we cannot reach them safely, does humanity's dream of building a home on the moon collapse before it even begins? These places are known as permanently shadowed regions, or PSRs, and they lie near the moon's north and south poles. Unlike the familiar equatorial plains that swing between scorching heat and deadly cold every 2 weeks, PSRs never see the sun at all. Because the moon barely tilts on its axis, the rims of certain polar craters block sunlight completely, leaving the floors in eternal darkness. Inside, the temperature falls below -200 degrees Celsius, colder than distant Pluto, colder than anything we could ever create on Earth. They are silent, airless, and blacker than the void of space itself, yet beneath that endless darkness lie glittering deposits of ancient ice. Scientists once called them natural freezers, but today, we know they are far more dangerous than anyone imagined. Here is the terrifying truth. The sun constantly blasts the moon with a stream of charged particles called the solar wind. These particles are mostly electrons and protons, but the electrons are much lighter and faster. When they slam into the moon, the electrons easily race into the shadowed craters, while the heavier ions lag behind. Over time, this imbalance leaves the crater floors loaded with excess negative charge. Meanwhile, the surrounding sunlit ground actually sheds electrons, making the electrical difference even sharper. The result is a hidden electrical trap. In plain terms, each crater becomes a massive, invisible battery. That is what makes these regions so terrifying. They are primed to spark. And when that spark comes, the consequences are devastating. Electronics can burn out in an instant, spacesuits can jolt with dangerous currents, and lunar dust, the most hated enemy of every Apollo astronaut, can turn into a deadly conductor. In these conditions, hundreds or even thousands of volts could build up silently, waiting for the slightest movement to release them in a blinding discharge. On Earth, static electricity is harmless because our atmosphere bleeds it away quickly. But on the moon, there is no air, no safe outlet. The only release is through sudden arcs of electricity, powerful enough to fry delicate machines or even threaten human lives. Now imagine a human mission. A team lands near the rim of a polar crater, preparing to confirm once and for all how much water lies hidden inside. One astronaut carefully steps into the darkness, their suit packed with the latest life support systems and communication gear. The suit is built to resist radiation and extreme cold, but it cannot change the fact that it is an isolated shell in a charged environment. Step by step, the charge builds. Then, without warning, an arc leaps across a connector at their life support pack. Alarms scream inside the helmet. The astronaut feels a jolt and their breathing spikes. For a split second, they do not know if their oxygen supply has failed. Their crewmates freeze in horror as the signal crackles in and out. It is the kind of nightmare no one has prepared for, and yet it could happen on the very missions meant to secure humanity's future. Even if sparks never fly, the moon has another hidden weapon: dust. Lunar regolith is razor-sharp, clinging to everything it touches, and it already caused chaos for Apollo astronauts. They complained that it coated their gloves, shredded their suits, and jammed their equipment. Now imagine that same dust electrified. It sticks tighter than ever, finds its way into seals and filters, smothers solar panels, and may even float above the surface in eerie clouds. If dust this sharp and toxic ever leaked into a habitat, it could scar lungs the way fine glass shards would on Earth. If it clogs cooling systems, entire machines could overheat and fail. On the Moon, every single grain of dust is dangerous, and with electrical charge, it becomes a nightmare. So, the Moon's poles may hold the water that humanity needs to survive in space, but they are not safe havens. They are hostile, unstable traps where darkness hides new discoveries and great risks. And if these craters are so dangerous, how did the water get there in the first place? That mystery changes everything. The truth about lunar water. For most of the 20th century, scientists believed the Moon was bone dry. Apollo astronauts brought back rocks in the late 1960s and early 1970s, and when those samples were carefully examined, they appeared completely devoid of water. The conclusion seemed obvious at the time, with the Moon's lack of atmosphere, no magnetic shield, and extreme surface temperatures. But a single assumption can collapse quickly in science, and the discovery of lunar water became one of the most dramatic reversals in space exploration. Hints began to emerge in the 1990s when orbiters carrying radar instruments detected strange signals coming from the polar regions. Radar is sensitive to hydrogen, and some of these reflections suggested that the permanently shadowed craters near the poles might be hiding ice. At first, these results were controversial. Hydrogen can come from many sources, and radar echoes can be tricky to interpret. Was this truly frozen water, or something else entirely? Over the years, more missions joined the search. NASA's Lunar Prospector mapped hydrogen concentrations at both poles in 1998, giving researchers a clearer picture of polar cold traps where ice might survive. Then came the big breakthrough in 2009, when NASA deliberately crashed the ICROSS spacecraft into a crater near the South Pole. Instruments riding behind the impactor detected a towering plume of material, and inside it they found unmistakable signatures of water ice. In simple terms, scientists had thrown a probe into the darkness and the Moon spat out ice in return. Around the same time, India's Chandrayaan-1 orbiter used infrared spectrometers to detect water and hydroxyl molecules across the surface, even in regions exposed to sunlight. These missions shattered the old myth and forced everyone to rethink the Moon's history. Sample returns confirmed the story. China's Chang'e 5 mission brought back lunar soil in 2020 that contained measurable water content, though at levels far lower than on Earth. These samples, combined with reanalysis of Apollo rocks using modern equipment, revealed tiny glass beads and mineral grains carrying traces of water or hydroxyl locked inside. Such findings proved that the Moon was not just passively holding ancient ice in deep craters, it was an active world where water could form, move, and disappear. It was a revelation that forced scientists to ask a deeper question. If orbital sensors detect hydrogen, how do we know whether it represents actual water ice, hydroxyl, or just stray hydrogen atoms bound to minerals? Remote sensing can tell us there is hydrogen, but it cannot always reveal its exact chemical state. The surprises did not stop there. Instruments began to find signs of water even in areas exposed to direct sunlight, where temperatures soar to well above 100 degrees Celsius during lunar noon. How could water survive under such conditions? The answer lies in chemistry and timing. Protons from the solar wind constantly bombard the Moon's surface, and when these positively charged particles strike oxygen atoms in lunar minerals, they can form hydroxyl groups. Some of these hydroxyl molecules combine further to create water. When the sun rises and heats the surface, these fragile molecules can hop across grains of dust, migrate to cooler areas, or even escape into space, only for the cycle to begin again when the sun sets. This means that a thin, transient layer of water can form and vanish on a daily cycle, a dynamic process that no one expected on a supposedly dead world. It raises a haunting question. If water can appear out of nothing more than solar particles and rock, how much more might be waiting in places we have not yet explored?